Hi everyone, Professor Bob Young here. In this instructional video, we're going to discuss inverse trigonometric functions. So the objectives for this video is to understand and use inverse sine, cosine, and tangent functions. We're also going to use our calculator to evaluate inverse trigonometric functions. And we're going to find some exact values of composite functions with inverse trigonometric functions. All right, so here are some helpful things to remember from our earlier discussions from your old algebra / pre-calculus algebra courses about inverse functions. And if no horizontal line intersects the graph of a function, now remember a function passes the vertical line test. Now it has to pass both vertical and horizontal line tests more than once. Remember, this type of function is called a one-to-one function and has an inverse function. All right, so if the point xy is on the graph of the function f, then the point yx is on the graph of the inverse function donated f minus 1 of x. The graph of the inverse function is the reflection of the graph of the function about the line y equals x. All right, so here's our basic sine function graph that we've been looking at over the last several videos. Now notice this one, the horizontal line test shows if I go across here, whoa, this isn't one-to-one. So the sine function has no inverse. We're done with this section. We don't even have to worry about it. We're finished. No. So what they do in this case is, well, where is the sine one-to-one? And they went ahead and they said, well, if I were to take this area from negative pi over 2 to pi over 2, and I were to follow this part of the sine curve, would you all agree that this area passes both vertical and horizontal line test? So that's what we're going to focus on when we do these. So along this area, we can say that y equals sine x has an inverse function on this restricted domain, the x values from negative pi over 2 to pi over 2. The inverse sine function, again, donated by sine minus 1 of x, and I've also seen this called the arcsine in books, is the function y equals sine of x in this interval. So thus, y equals the inverse sine of x means the sine of y equals x, where negative pi over 2 to pi over 2 is your range or y values, and your domain is going to be between negative 1 and 1. So this is red now, y equals the inverse sine at x. And what I like to call this is the angle getter. Okay, one way to graph this is to take the points on the graph of the restricted sine function and reverse the order of the coordinates. All right, so what I like to do is I like to come over here, and if I'm graphing y equals sine x, or the function f of x equals sine x, let's look at that interval that does passes both horizontal and vertical line test, and notice the x values is going to be negative pi over 2, negative 1, 0, 0, and pi over 2, 1. So if you come over here and you're graphing the inverse sine, which is sine minus 1 of x, or sometimes people will call it the arc sine of x. I've seen this in both books to show or indicate inverse sine. Then remember, on inverse functions, y becomes x, x becomes y. On 0, 0, it's really not going to matter. So if you can graph the sine function, you can easily graph its inverse just by flipping the x and y values. Also note that the domain of the sine that has an inverse, the inverse qualities we seek, is negative pi over 2 to pi over 2 with a range of negative 1 to 1. And the inverse sine has a domain of negative 1 to 1 with a range of negative pi over 2 to pi over 2. So again, the x and y values are interchanged. Now, another way to obtain the graph of y equals inverse sine or arc sine x is just to take the graph of the sine, which is here in red, and reflect it about that line y equals x. And also on inverse functions, if you remember from previous courses, if you do the composite functions, the fog and the goth, the f of g of x will come out to be x, and g of f of x will come out to be x, as indicated as this reflects about the line y equals x. All right, one important point to make here is when we're finding these values for the inverse sine, I'm going to go ahead and put the unit circle back up here, ladies and gentlemen, because I've always been an advocate of knowing the circle here. Now notice the inverse sine only exists on the unit circle between pi over 2 to negative pi over 2. So if we put the circle back together in that area that we have these restrictions, really, when we are after angles here, we're only going to be after angles that's in the first and the fourth quadrant. So what we did down here is we spelled out the possible answers of any inverse sine that are going to be exact angles here. And then we can get the ones in between negative pi over 2 to pi over 2 on our calculator. And remember, the decimal approximation here would be negative 1.57 to 1.57, and we'll look at some of those later. All right, so remember that if you have the sine of theta equals the inverse sine of x, if you were to go ahead and take the sine of both sides of this equation, remember what happens when sine meets inverse sine. I always like to say inverse is something, the word I like to use for inverse functions in my videos in algebra is undoes. I don't even know if that's a word or not. The comm teachers may get all over me, but when a sine hits an inverse sine, it undoes it. So you end up with this angle here, x, equals the sine of theta here. And again, we're in this restricted area between negative pi over 2 to pi over 2. All right, now it can be negative pi over 2 and pi over 2. So we're going to go ahead and look at a few of these as we progress. All right, so we want to find the exact value of the inverse sine of the square root of 3 over 2. Now, what I like to do with my students is, one, go ahead and let that angle theta equal the inverse sine of x, which in this case is the square root of 3 over 2. And we're asking at what angle is the inverse or the sine equal to the square root of 3 over 2. So if we go ahead and rewrite this, we're saying at what angle is the sine the square root of 3 over 2. And I always like to draw a circle up on the board here. And what we're looking at here on this circle is, well, the sine is the square root of 3 over 2 at this angle, which is going to be pi over 3. So that would be the answer. So that's how I like to do it when I'm working on these. All right, so notice the chart across the bottom here will verify that. So at what angle is the sine equal to the square root of 3 over 2? It's at pi over 3, the angle here. All right, let's try another one. Find the inverse sine of minus square root of 2 over 2. Again, I'm going to draw me a quick circle here. And these don't have to be real pretty here. I mean, just get an idea. Now remember, we can only go fishing between negative pi over 2 and pi over 2 on this circle. So where is the sine going to be negative? And that square root of 2 over 2 should ring a bell for you down here. All right, so again, if you know your unit circle, these become much more easy to get. So what angle are we looking at here between negative pi over 2 and pi over 2? I would say the answer is negative pi over 4. So let's go ahead and look at the remainder of this. All right, so let theta equal this, as shown. Go ahead and rewrite it. You can take the sine of both sides to undo the inverse sine and rewrite it if you wish like this. At what angle is the sine going to be minus square root of 2 over 2? And then You can look at the values between there, but if you know your unit circle, folks, this is going to be a whole lot easier again. And here is where we're at. See, I like to just draw the circle when I do these, and maybe you'll get in that habit too. We'll see. All right, next up to bat, we're going to look at the inverse cosine function. So we've got the cosine function here that we have graphed in the past, and it says the horizontal line test here shows that the cosine function is also, if we went across here, not 1-to-1. So where is it 1-to-1 at? Well, on the cosine function, they chose the x values between 0 and pi radians here. So they're looking along this part of the curve. So the inverse cosine function donated by the cosine minus 1 of x or the arc cosine of x is the restricted cosine function y equals cosine of x for this x interval 0 to pi. So thus y equals the arc sine or the inverse sine of x means the cosine of y equals x, where y is between 0 and pi, the range, and the x is between -1 and 1. And we'll do a similar argument that we did with sine on cosine here. So again, if you wanted to just take this part of the curve that is 1-to-1 and passes the horizontal and vertical line test, notice we could take the 3.01 pi over 2, 0, and pi -1 here, and we can just interchange the x and y values, and here is what the inverse cosine looks like. And notice again, the domains and the ranges have interchanged. And we're going to solve these the same way. We can let theta equal the inverse cosine of x, so we can take the cosine of both sides and rewrite this as x equals cosine theta, where theta must be, of course, between 0 and pi. Now let me show you something on the inverse cosine that's a little different here. If we're looking at the inverse cosine, the x values go from 0 to pi. So we're going to look at all of these angles between 0 and pi in the first and in the second quadrant. Now remember, the inverse sine only existed from -pi/2 to pi/2, which was in the first and the fourth. The inverse cosine, however, because of the cosine graph, remember it has that 90-degree or pi/2 shift. So we're really only going to look at these angles. This will be the answers for most inverse cosines that are exact. And we're going to continue our discussion as we look at some of these examples. So it says find the exact value of the arc cosine of -1/2 or the inverse cosine of -1/2. Now again, you can do it by letting theta equal this and go forth with that. But let me show you what I like to do. I like to draw that etched out circle here, and I'll say, where is the cosine -1/2 here? And I would have to think it would be, well, I'm having to look now from 0 to pi, and cosine's negative over here. And if you think about that, for those first quadrant angles here, I think we're going to end up with the cosine -1/2 at 2 pi over 3. All right, so let's see if that's true or not. All right, so the steps, let theta equal this. Go ahead and take the cosine of both sides of the equation, and you can rewrite it as the cosine undoes the inverse cosine here, and you will have x equal, or theta equals the inverse cosine of -1/2 will become the cosine of theta equals -1/2. And then if you look at the chart here, well, where is the cosine going to be -1/2 at? And there we are at 2 pi over 3. So knowing the circle can save you some time. So the angle in between 0 and pi where the cosine is -1/2 is here. All right, let's look at the inverse tangent function here. Now here's the tangent graph. And remember, it goes on forever and ever in both directions. Now, the only place that passes both vertical and horizontal line test is this piece here in the middle. All right, so this is the piece that's 1 to 1 in here. And notice this happens between negative pi over 2 and pi over 2. So the inverse tangent function, denoted by tan minus 1 of x, or arctan, is the restricted tangent function y equals tan x. Of course, x happens between negative pi over 2 and pi over 2. And again, if you take the tangent of both sides of this, you'll get this. The tangent will undo the arctangent and so forth. And then you'll have y between negative pi over 2 and pi over 2, and x between negative infinity to infinity here. So again, if we were to graph the tangent graph here in the arctangent graph, let me show you what I would do. All right, notice here at negative pi over 2 and pi over 2, the tangent's undefined. We've discussed this in prior lessons. And the values between those are the good, nice tangent values. So at negative pi over 4 or at negative 1, the tangent of 0 is 0. And at pi over 4 or at 1. So if we flip these values here, x becomes y, y becomes x. Watch what happens here. Again, the 0, 0 doesn't do much. We have this graph where now the y values here are between negative pi over 2 and pi over 2. So the asymptotes actually flipped around here on the inverse tangent. And the x values go from negative infinity to infinity, while the y values on the arctangent stay between negative pi over 2 and pi over 2 radians. So again, looking at the inverse tangent graph, which we were looking at earlier, when we are after answers, we are going to get angles in here, similar kind of like the sine. The inverse sine from negative pi over 2 to pi over 2. Notice that the tangent can't equal negative pi over 2 to pi over 2, where the arc sine could, and you're going to end up getting some interesting values here for the angles. And boy, the inverse tangent ones bother people because they forget their circle and the xy value, so you have to be kind of careful on this one. All right, let's find the exact value of the arctangent of negative 1 here. So in other words, at what angle is the tangent equal to negative 1? So I'm going to draw me a little unit circle here. And notice the tangent graph, folks, also similar to the inverse sine, stays in this first and fourth quadrant from negative pi over 2 to pi over 2, where the inverse cosine was 0 to pi. So if you're kind of thinking about things here, you might want to come over here and say, well, the inverse sine can be answers between here, angles between here, as the inverse tangent is, except the inverse tangent can't equal negative pi over 2 to pi over 2. Now, where is the tangent negative 1? Well, the tangent's positive in this first quadrant. It's negative down here, and it's only negative 1 wherever the sine and the cosine are the same values, but opposite things here. So I would say this answer would be negative pi over 4. Now, if you want to do this by letting this be theta, we'll do that as well. All right, so we can let theta equal the inverse tangent of x, and we can go ahead and rewrite this theta equals inverse tangent of x as the tangent of what angle equals x in this restricted area here, this restricted domain. So we can say at what angle is the tangent negative 1, and that would be here at negative pi over 4. So the angle in this restricted interval here, whose inverse tangent is negative 1, would be the angle pi over 4. And you could check that by taking the tangent of negative pi over 4, and that would come out to be negative 1. All right, so here is the graphs of the 3 basic inverse trigonometric functions: the inverse sine, as we discussed, domain and range, the inverse cosine, notice this one's a little bit different, and the inverse tangent, how they all appear. Now let's go ahead and use a calculator to find the value to 4 decimal places for each function. Now make sure your calculator is in radian mode here. So what you're going to have to do is put it in radian mode, hit the second button and cosine, and notice the inverse cosine there should be right with your cosine button, but you'll have to hit second inverse cosine, type in 1/3, and just like it looks here, I would put parentheses around the 1/3. Your calculator may automatically do that, it may not. And you should get this value, 1.2310, approximately, rounding that. All right, so make sure you can. The inverse tangent, let's find example B here, the arctangent or inverse tangent of negative 35.85. And we'll go ahead and hit second tangent, put that in. You should get approximately negative 1.5429. So here are the inverse properties, the sine function and its inverse. So if you take the sine of the arcsine of x or the inverse sine of the sine of x, you're going to get x. And this is what I call the undoes mode. But again, you only have these restricted intervals for every x from -1 to 1. On this one, for every x in the interval -pi/2 to pi/2. So you have to be real careful here. And similarly, the cosine of the arc cosine or inverse cosine and vice versa comes out to be x in these restricted areas, as does the tangent here. Now, the tangent one here, it could be all real numbers for the bottom one down here, because that tangent, inverse tangent, looks like that. All right, so we're going to find the exact value of possible of the cosine of the arc cosine of 0.7. And if this is in that restricted range, you won't believe how easy this is. You will get that answer. The inverse sine of the sine of pi is going to be 0. Now remember, the sine of pi is 0, so the inverse sine of 0 would be 0. But watch out for this one. See, something smelling fishy here, because if they ask you for the inverse cosine of some negative value, -1.2, -1.2 is not in the domain of the inverse cosine and is not defined. So if you try this one on your calculator, it is not going to be happy. So that concludes our video for inverse trigonometric functions. I hope that these objectives were met. And now it's time to hit those assignments. Good luck.